Okay, so before we do any sort of function problems or even learn what an actual function is in math, we need to briefly understand what a Cartesian product is. So what is a Cartesian product? Well, a Cartesian product is when you take two sets. For example, let's take the sets A and B, and what you say is A cross B. Now, what does this notation mean? Well, it means it's the set of all ordered pairs x and y such that x is in A and y is in B. Now, I use the word ordered pair. What does that mean? Well, it means when you take an element in A, that goes first in your bracket here. And then you pair it with an element with B down here. You cannot take an element in B on the left-hand side and then put down the element in A. So you cannot say y comma x. This is not correct for A cross B. If we wrote instead, for example, something like B cross A, then this would be, in fact, the set of all ordered pairs yx such that y is in B and x is in A. So it would be a completely different type of Cartesian product if we switch those around. So the order in this case absolutely matters. Now, I've just given you a mathematical definition, so maybe you don't quite see what this actually is. So let's take an example. Let's let A be the set containing 1, 2, or let's just have it contain the elements 1 and 2, and let's have B contain the elements A and B. So then when we take the Cartesian product of A cross B, what that ends up being is a huge set. It's a set, remember, that's what this definition means. It's a set of the ordered pairs. So take an element in A, let's take, for example, 1, and you pair it with an element in B, so let's take A. Then, because it's all of the ordered pairs, so it means we have to pair 1 with everything, 2 with everything, and write all of those down. So we've already paired 1 with A, next we have to pair 1 with B. Awesome. What's left for our ordered pairs? Well, we've done everything. We've done all the ordered pairs with 1. Now let's do all the ordered pairs with 2. So then we say 2 comma A. We've paired it with the first element in B. And then we can finally say 2 comma B. So this would be the Cartesian product of these two sets. Now what do we notice here? Well, we notice that, of course, as I've already mentioned, you have to pair everything. You cannot just say, oh, it's going to be these two ordered pairs. No, you have to write every single possible ordered pair for this example. Another way to have visualized this is the following. Okay, just have to quickly write that down. A way we oftentimes visualize a Cartesian product is we draw this. We draw a line for our A. Usually what's on your left-hand side, you draw the horizontal line. And then for your vertical, you draw your B. And then you say, okay, let this be 1 and this be 2. Let this be A and let this be B. And then your Cartesian product is going to be everything that lines up here. So what you find is when you visualize a Cartesian product like this, all of the ordered pairs are going to be all of your intersections for all of these. So as you can see, 2 intersects with A and 2 intersects with B, like we have down here, and 1 intersects with A and 1 intersects with B. And those are the only intersections we're able to make, and we notice there's 4 of them, which exactly matches how many ordered pairs we're able to write down, which is in fact 4. Let's take a slightly more complicated example. Okay, so in this case, our two sets are going to be the set A containing the elements 1, 2, 3, 4, and the set B containing the elements 1, 2, 3, 4. So what is A cross B going to be? Well, it's going to be the set containing all of the ordered pairs with 1, all of the ordered pairs of 2, 3, and 4 that match with B. So this is going to be a very large amount of ordered pairs. So instead, let's visualize what this is going to look like. So we say We draw a horizontal line for our A, and we can mark down the elements like so. This is going to be our 1, 2, 3, and 4. And then similarly, we can write down the elements for B on our vertical line. So we say 1, 2, 3, 4. And then we sort of like visualize like these imaginary like dashed lines that you can have, right? For each element. And then what we want to do is we want to count how many times they intersect. So we notice 1 intersects with 1, 1 intersects with 2, 1 intersects with 3, and 4. So when you take the element 1 in A, it has 4 ordered pairs with the elements in B. Similarly for 2, 2 also we will find has 4 ordered pairs, and 3 has 4 ordered pairs, and 4 has 4 ordered pairs. Maybe it'd be better if I write this in crosses and get rid of these lines. Okay, so I've just gotten rid of some of the dashed lines, and I've turned my dots into crosses so you can more easily see. So we notice that A has 4 ordered pairs, 2 has 4, 3 has 4. So all we have to do is count up how many of these ordered pairs there are. Well, there is 4 times 4, which is going to be 16. So A cross B in this case has 16 ordered pairs, or the size of A cross B is going to be 16. Now, another point I want to make is that the number of ordered pairs you're going to have, you might be noticing so far, is it's going to be equal to the number of elements in one set multiplied by the number of elements in your other set. So, for example, B here, it has size 4 because it has 4 elements. And A here also has 4 elements, so it also has size 4. So to find how many ordered pairs you get when you do A cross B, it is going to be the size of A multiplied by the size of B, which is going to be 4 times 4, which is going to be 16. So that seems to work. Now, so far I've been taking A and B to be the same size. These sets do not have to be the same size. So for example, if I were to get rid of, let's say, the number 4, and our set B just contains 1, 2, and 3. Well, in that case, we can erase this top line up here, and this is all our Cartesian product is going to be. So we then replace this 4 with a 3, because B now has size 3. And we find that we should have 12 ordered pairs, because the size of A is still 4, the size of B is 3, 4 times 3 is going to be 12, and is that true? Well, let's see, we've written out all of the A and all of the B, and we've taken the Cartesian product, so we find 1 has 3, 2 has 3, 3 has 3, and 4 has 3. This is going to be 4 times 12, which is exactly the answer we got here. So this is how you can find out how many ordered pairs your Cartesian product is going to have. Now, something some of you might have already begun to notice is that a Cartesian product looks a lot like a grid system, right? It looks like we're creating a grid here. It looks a lot like a graph almost. And you would be right, that's a lot of what a graph actually ends up being. A Cartesian product, something that we're all familiar with in reality, is actually the Cartesian product between the sets of the real numbers and the sets of the real numbers, which is just going to be the x-axis and the y-axis, where you can have decimal numbers, integers be on your x, and similarly for the y. That is the typical Cartesian product everyone is familiar with, the x and y axis. So in this case, it would be just the set of all the r and the set of all the r in both of them, right? So you would get rid of all of these points. You'd get rid of all of these labels here. This would still be A, this would still be B, but this would just be all of the real numbers along this, which there's an infinite amount, so we can't really discretely write them all down. Similarly for A, so what you end up getting is almost like a box that is filled in and has no edges, but of course I can't draw that, so I'm just going to add these arrows here. So you're already familiar with the Cartesian product. It's just like a graph almost, Or in this case, it would be between the sets that have real numbers, which would just be a typical graph. If you made this the set between integers, like so, we wouldn't have this continuous blob. We would go back to having our concrete points on our Cartesian product visualization. We would have 1, 2, 3, 4, 0, 0, 1, 2, 3, and then you would have discrete points, right? And of course, these would all go on forever, and you would also have negative numbers in both directions. So that is really what a Cartesian product is, and that's also why it has to be an ordered pair, because think of it like the graph. You can't just switch the y and x values without it having some consequences. So in this case, we're saying whatever is in A has to be your x, right? So if we choose our A to be 2, we have to go along with the x on the 2. And then we have to pair it with something concretely in our B, which is going to be our y. That's why you can't just switch them around. So there we go. That is what a Cartesian product really is. One more point I'm going to make. So about the ordered pair part, because that is super duper important. Let me quickly rewrite the example I just did. So this is the example we just did. Why should you not just carelessly flip the x and y values here? Well, because let's say we wrote down B cross with A. What would that in fact look like? Well, it's going to look like this. Our B is going to be down here with our 1, 2, and 3. Oh, that's a 2. Should be a 1, 2, and 3, and our A this time is going to be vertical. It's going to be 1, 2, 3, and 4. And what you find is the number of ordered pairs is going to be the same, but when you look at your graph, quote unquote, it's going to be different. Notice how in this case we have more on the x-axis, whereas in this case we have more on the y-axis. So the order absolutely matters in your Cartesian product.